molecular size for boiling points. That's an easy numerical response question when we talk about the size of organic molecules. Okay, so extraction processes. So here's the deal. Oil and natural gas come from aquatic resources, so you should know that. All right? So oil and natural gas mostly come from planktonic organisms, so zooplankton and phytoplankton, so things that are suspended in a water column, all right, in sedimentary rock layers. So oil and natural gas come from old oceans. So Alberta has a lot of oil and natural gas because most of Alberta used to be an inland ocean. So during the late Cretaceous and the geological periods where dinosaurs existed, and before that, actually, most of our oil and gas was deposited before dinosaurs were around in the Devonian period. All right. So we had, we called that the hothouse Earth period of time, and we had big swampy areas with large ferns during the Carboniferous period, which deposited a lot of our coal. And a large part of Alberta was a lot of Alberta was an inland ocean, and that's why we have the prairies here. Because it was an old ocean bottom, and that's why we have formations like the Badlands, like the Drumheller formations. Those are old reefs formed from aquatic resources. So, oil and natural gas come from ancient aquatic organisms, and coal comes from terrestrial organisms. So, what you need for oil and natural gas to form is you need decomposition inside sediment where there's no oxygen. Okay? You need alternating porous and non-porous bedrock. So what you need is a place for the hydrocarbons to percolate through and then get caught. So you need sedimentary and igneous rock combining. So you need layers of them alternating, and that forms petroleum traps. You need low oxygen levels, and you need high pressure and temp, and you need lots of time to form fossil fuel plays. Okay. So on page 362, you have stratigraphic traps of different types of oil and gas plays. So this is figure, right? So these are common petroleum traps. So this is a limestone reef trap. This too is a stratigraphic reservoir, typical of what we would find in Turner Valley. This is a petroleum trap that we would find in Saskatchewan. This is a fault trap. So this is a fault line where two tectonic plates are combining, and this is a displacement trap. Okay? Now you have the different types of resources that are available here: gas, oil, water, and then your different types of rocks as well: sandstone, limestone, etc. Okay, so you need alternating porous and non-porous bedrock, you need interaction of tectonic plates, and you need time to create these. So make sure you take a look at that on page 362. I'm going to show you another image here. So this is an image, it's kind of a cross-section of the province of Alberta. So if we were to look at the province, kind of from the topsoil layer down, this is the Rocky Mountains to the west. So this is I need a pointer here. So this is the Rocky Mountains to the west, and the foothills are right here. So Cochrane, would be kind of here, right? So, and then this goes east, all right? So this goes east across the province, and these are our bedrock layers from west to east, okay? So this shows us where we find different types of hydrocarbons based on the bedrock available. So I'm looking, if I'm a geologist around here, I'm looking for Devonian rock. Okay? That's where most of my oil and gas plays are going to be. So you can see that we have to go through. So this is a Cretaceous bedrock layer. This is the Tertiary period so this is rock layer that's been deposited since the age of the dinosaurs ended. This is Cretaceous bedrock, and this is sedimentary rock deposited from inland oceans. Most of our oil and gas plays are from the Devonian era during the hothouse earth period. And then all of this sits on top of a large supervolcano which created the Cambrian shield rock, all right, or the Precambrian shield rock. So this is kind of the anchor of North America, is this Precambrian shield rock. So we don't have a lot of Canadian shield in Alberta. So if you see this here, this is where the shield rock permeates. Now, if you think about the landscape that's over Precambrian rock, it's mostly boreal forest, okay? It's igneous rock, so the soil layer isn't very high. So coniferous trees are about the only thing that can exist there. So if you kind of drive through northern Ontario, you get up north of Saskatoon and into Prince Albert and Prince Albert National Park, and north of that at northern Saskatchewan. Most of Ontario and Quebec are Canadian shield, and then east, if you end up driving across Newfoundland or something, that's an island that's broken off from the mainland, but that's a good example of what a Canadian shield landscape looks like. So here's the deal: is we have the North American plate and the Pacific plate colliding to create the Rocky Mountains. And this causes all this crustal uplift from this sedimentary rock. Now, what happens as the shield rises is all this sedimentary rock created by the crustal uplift from the Rockies, what it does is it squeezes against the shield in the northeast part of the province. This is actually where Wood Buffalo National Park is. This is the largest national park in the world, right? And it's north of the main oil sands extraction sites. So the reason why we have oil sand in Alberta is because all of this sedimentary rock from previous geological eras is combining with this ancient Precambrian shield volcanic rock. And this is igneous rock, and it's very, very hard, all right? And then this is sedimentary rock that's squeezing against this impermeable rock. And what happens is the oil and gas resources get squeezed to the top of this sedimentary rock, and that's what creates the oil sand. So from the pressure, the oil is squeezed into sand and water, and then it comes to the surface, and that's why we have oil sand. So it's that combination of the crustal uplift from the sedimentary rock being squeezed against the Cambrian shield in the northeastern part of the province. So I need to know my geological layers to know where I can drill for oil. So that's how we get oil sand. Now, in this, if you live in Alberta, you should know how oil sand is extracted. All right? So the oil sands, right in the northeastern part of the province, they cover an area the size of Greece, essentially. Now, most of our production does not happen with this open pit stuff. So this is the stuff that people like to protest. All right, so this is an open pit mine. That's only about 20% of our production of oil sand. Okay? So if the oil sand is less than 70 meters below the surface of the earth, it makes more sense to use a mine like this and then scrape the top soil layer off. The industry calls this overburden, which a lot of environmentalists find offensive, right? But the open pit here is only about 20% of our production. most of our production happens this way. This is called steam-assisted gravity drainage. All right. A good example of this is the Christina Lake production facility northeast of Fort McMurray. Okay, so what happens here, this is called in situ or SAGD. So this is most of our production of oil sands. So what happens is we inject superheated steam, it's about 400 degrees Celsius, into an oil sand play. And what that steam does is it separates the bitumen, which is the oil itself, from the rock and sand, and then we pump that slurry out, and then it's separated at the actual plant itself. So we use this horizontal drilling technique. We inject steam in, and then take the bitumen out. It's kind of like hydraulic fracturing, but it's a little bit different. Okay? So the way we do this is called the Clark process. All right? Now, we're not the only place on Earth that has oil sand. This is used in Utah. Venezuela has oil sand as well. But the Clark process was actually created in Alberta. Right? So take a look at this slide. You have a separation of the raw materials with steam, and then we have further refining that happens there. Okay, so what we actually get once we've successfully separated the oil from the sand, right, is we get, this is bitumen, right? So that's bitumen, and it's really, really viscous. Right, so this is upside down right now. It's viscous. It's thicker than the consistency of molasses. So that's the stuff that we're taking out of the oil sand. Now this stuff doesn't flow through pipeline really well, so we have to heat pipeline in order to bring it to a heavy oil refinery. So it's a very energy intensive process. In fact, our bitumen pipelines are heated by natural gas. So it takes a ton of carbon to extract and move bitumen. Right? So again, that's why there's a lot of resistance to wanting to try to further develop that resource. Okay. So this slide you can't see that well. This is slide 15. So be familiar with the oil sand extraction process. We use the Clark process to separate, and then the oil sand is upgraded and finished into a crude product on site, and then it's shipped for refining later. Okay, so excuse me, natural gas is our most abundant resource in Alberta. So natural gas is mainly methane. It's extracted by conventional well methods or by hydraulic fracturing. So what we do with hydraulic fracturing is we put pipes into a natural gas play in sedimentary rock. The pipes are encased in concrete, and what we do is we send what's called a frac flurry, a hydraulic fracturing slurry with frac fluids down into sedimentary rock that basically sandblasts and blows out the little cracks in the natural gas well, and then all the natural gas can be collected from a single well as a result. Right, so we get it piped to a processing plant after that. The problem with hydraulic fracturing is it's often above the bedrock. Sorry, it's above the water table. So as we crack the natural gas well, methane can percolate into the water table, and that causes water security issues. Obviously, it also causes earthquakes. Right, so my brother has caused a few earthquakes working on the Montney Shale in Grand Prairie for that. And the frac fluids are proprietary to the companies, so they're full of chemicals, and they're going down into the wells, and a lot of people don't even know what they are, right? So, they're strong acids and strong bases, and they're used to remove heavy hydrocarbons. So when we look at natural gas, most gas in Alberta is sour, meaning it's full of hydrogen sulfide. So when we sweeten gas, we remove the H2S. So we use a nitrogen-based compound called diethynylamine, so diethylamine, to do that. So it's an alcohol-based compound with nitrogen. So water, liquid hydrocarbons, and CO2 are removed. The H2S reacts with oxygen in an absorber tower to form sulfur dioxide. All right, so we're going to remove all that extra stuff. The hydrogen reacts with oxygen in a natural gas tower to form sulfur dioxide. We make H2S and SO2 left over from the sour gas process. They're piped to a part of a natural gas plant called a Claus converter. We recover the hydrogen and oxygen and then convert the waste products to elemental sulfur. And that was that big sort of sulfur pile that you saw, that picture that I took when I went up to the oil sands. So sweetened natural gas is a combination of a few elements. You should take a look at page 363 to look at what natural gas is composed of. So there's some nitrogen, carbon dioxide, methane. It's mostly methane. There's a whole bunch of different things, though. Okay? So just take note of that. So you've seen this along the landscape around here in Cochrane, right? There's a gas plant. There's the Shell gas plant, right, just west of St. Tim's. There's the Wildcat Hills gas plant on the way to Morley. On your right-hand side is an absorber tower. And right, so the absorber tower itself removes the H2S to make sulfur dioxide. And then the Claus converter recovers the hydrogen and oxygen and then removes the waste products, which would be the sulfur. It turns the sulfur into elemental sulfur. So we use centrifugation and we use catalysts to do that. Okay, so those are your big things that are in a natural gas plant. The last big hydrocarbon that we have is coal. You can see the homework, page 361, number 6, page 364, number 3 and 4. Coal comes from terrestrial resources. All right? So coal generally comes from swamps and bogs, marshes and fens. Most of our coal came from the Carboniferous period of geological time. Okay? So it's mainly carbon. You have two types, lignite or anthracite. Anthracite is a bit denser than lignite. Coal will have sulfur, nitrogen, oxygen, and hydrogen, so it'll have a lot of the same impurities that natural gas does. Pressure, heat, and time convert the terrestrial resource into coal. All right? So they come from standing water. So you can see bog, marshes, fens. Now, fens are wetlands that are created from natural springs. And peat, right, is anoxic, decomposed marshland, right? Peat houses a ton of carbon. So as we burn peatlands, we release a ton of carbon into the atmosphere. So this is happening with, there's lots of peatland being burned in Indonesia and Borneo and places like that to make room for palm oil plantations. That's a really big problem right now. So we're phasing coal out, right? And by 2030, Alberta will not be using coal as a form of energy production. So one thing we should also understand about our oil sands resources is that there's a lot of oil sands resources. We have a ton of it. So there's about 1 trillion barrels of oil in the oil sands right now. And if we were to extract every last barrel of oil from the oil sands, we would be able to fuel the world economy for the next 700 years. So people saying that oil is going to run out is true. It's just not going to happen in the next couple decades. It's going to happen in the next couple centuries. The bigger issue with extraction of hydrocarbons is we need to move away from them relatively quickly in the next couple decades because of climate change reasons, not because we're going to run out of oil and gas. So just from the oil sands alone, we could fuel the entire world economy for centuries. That's not even considering other types of hydrocarbon resources elsewhere in the world, right? So, but we need to transition away pretty quickly if we're going to avoid massive environmental change like sea level rise and destabilization of local climates, which is already happening. Anyway, functional groups in organic chemistry. There's a whole bunch of them here. Okay, this is, you can look at this, but we're going to learn about alkanes. We're going to learn about alkenes, alkynes. We're going to learn about alcohols. We're going to learn about carboxylic acids. We're going to learn about esters. We're going to learn about amines in Chem 30. And that's about it. So all of these other ones you will learn in a higher level of chemistry. All right. So that's kind of the introduction. That's our discussion about extraction processes and things like that. I'll actually talk about how we name things in the next lecture. I'm going to sign off now. Have a good one.